Good evening.
How's it going?
I'm doing well. How are you?
Good.
Good. All right. A few people still coming in here, I guess. See, yep, I hit the recorder. Okay, so we are rolling. So tonight we're going to move away from rectangular beam analysis and rectangular beam design, and we're going to dive into one-way slab design for tonight. Before we do so, does anybody have any questions they'd like to ask of me? Okay. I do admit, I apologize, was a little tardy. I was out up in the high desert preparing for a test on most of Tuesday. We had our class Tuesday night, and then all day yesterday, I was up at Adelanto, which was a wonderful experience working outside yesterday in the high desert. So I was a bit tardy on posting homework number 2, but homework number 2 is posted now. That is due next Tuesday at midnight. And I also posted my solutions, which may or may not be perfect. Well, no, they're not going to be perfect, but hopefully they're good enough. But my solutions to homework number 1 have been posted as well. So any questions anybody has before we get rolling? All right. So.
Actually, Professor, I do have one quick question.
Sure.
Do you offer corrections for the homeworks as well?
Do I offer?
Or, well, not. Never mind. Actually, that wouldn't even make sense because you post the solution, so corrections wouldn't be there.
So what I do though is I do grade the homeworks. Hopefully, I'll get to homework number 1 this weekend. But what I do is through Blackboard, and this is not the best solution. I am not a huge fan of Blackboard, but through Blackboard, what I can do is grade the homeworks that you've posted to Blackboard, and I can put little comment stickies where I took points off. I can put a quick little comment as to why I took points off. So that's kind of your feedback that you'll get on your homework.
Okay.
Okay. And thank you for reminding me. I forgot to mention this. I'm trying to remember to click for each one of your homework assignments. I click that the homework does not count towards your grade. And that is only because the past classes that I've been teaching through Blackboard, some students have been sadly misled in the grade that they were carrying in the class because Blackboard was automatically adding everybody's grade out of the total to come up with like a running letter grade. That was absolutely and totally wrong because it wasn't weighted, see. So each homework was weighted equally to each midterm and the final. And that's not the way we grade the class. I mean, the homework is weighted at 20 or 30%, depending on the class, and the midterms are weighted at 30 or 40%, depending on the class. So trying to not mislead, I clicked on the little thingy that hopefully when I grade the homeworks, it doesn't add them to your grade at all. So you may all be carrying a 0 out of whatever through the course because I'm trying not to mislead that way. But anyway, the message is do not look to Blackboard for how well or how not well you're doing in the course. Do not look to Blackboard. Do not look at, well, Blackboard says I'm getting a B+. Don't look at that at all. That is totally fictitious because Blackboard has no clue. how the class is weighted. Okay, is that clear for everybody?
Yes, it's clear.
Great, perfect.
I have a question, Professor. Are you planning on staying on Blackboard or do we go to the Canvas?
I will. I am not planning on going to anything new,
Okay.
and I will tell you the microsecond we are allowed to go back to Cal Poly and actually do class the real way, I'm ditching Blackboard in a heartbeat. So, if that answers your question.
Okay, because I have other classes that they're on Blackboard and they're planning to go on Canvas since we're doing Canvas now for some reason.
I'm sorry.
I mean, it's
yeah.
okay.
I don't like any of them.
Yeah.
I don't like any of them. I'm old, people. I'm getting older and older. I like grabbing homework and using a big red pen and grading homework. I like having the test taken in front of me with a calculator, and I grade them with a big red pen. That's just the way I do it. But anyway, no, I hopefully it will never be going to Canvas, and hopefully we'll never be using Blackboard again. That's my position at this point in time.
Okay, thank you.
Sure. Any other questions? All righty. Well, if anybody has a question that pops up, please feel free to ask it as it pops up. I just remembered, this is how scatterbrained I've been this week. I just remembered we didn't finish our last lecture, so we need to do that first, don't we? So let me bring that one up first. We were talking about beam design. We were down here someplace. Okay. And slideshow from the current slide. Okay, why are you not working? Bear with me a second, having technical issues. Why are you not? There we go. Okay. Can everybody see the screen that says example 4?
Yeah.
Okay, great.
Yes.
Great, thank you. Simon, you had a question, I see. Can we get multiple submissions for homework? No, I don't do that because I grade the homework. So the homework is, there's going to be 8 homework assignments. Every homework assignment is due on Tuesday at midnight, and I grade those. So those homeworks are worth 20% of your grade. So does that make sense, Simon?
I think what he meant is like if we can resubmit it, like if it's not on due yet.
That gets really tricky because Blackboard only allows 1 submission. And so if you found a mistake and you need to resubmit, you'd have to email it to me. And that gets really cumbersome to try to keep track of who's on Blackboard
Yeah.
and who emailed me stuff. And it's likely I'll forget. So I would say for all intents and purposes, please double check it before you send it. And you get 1 shot with Blackboard.
Okay.
Okay. All right. So we didn't quite finish up last time. And let's get going on that. So the last example from last time we have a beam where the depth, the width, and the steel are all not known. So there's 3 unknowns. And this beam's going to take a pretty big load, 1,500 kip feet. We're going to use 4,000 PSI concrete. We're going to use 60 grade steel. And we're going to use these as our targets. So remember, if you have more than one unknown, you have to have some kind of a target to try to guide you into the right solution. So for this example, again, we're going to try B is less than or equal to half of D, and we're going to target epsilon sub T at 0.075. From table A.7 for grade 60 and F prime C equal to 4,000, we get rho equal to 0.138. And this 0.138, let me clarify that. Let me open the text. If you have your text in front of you, please open to table A.7.
Professor, I have a question. Quick question.
Sure, sure.
Those assumptions are consistent?
No. But that great question. No, those assumptions are not consistent. You mean that there's that B equal to half a D is a common, or epsilon T is 0.075 is common, or that it has
No,
to be?
I mean, if we have like 3 unknowns, depth, width, and steel area, if we assume those assumptions always, or
The answer is no. No. You could have an assumption of B should be 3/4 D and epsilon T should be 0.005. You could have a totally different set of assumptions. If you have 3 unknowns, then you need 2 assumptions to guide you. So that's consistent. That I'm giving you 2 guides for 3 unknowns is consistent. But the half D and epsilon T equal to 0.075, it could be anything I make up,
okay.
right? I could have said 0.005. I could have said 0.1. I could have said B equal to D. No, those are just subjective, and I just made them up for this problem.
So basically, if we see at the end that those assumptions are wrong, we start all over again with the different assumptions. That's how it goes?
No, 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 no. Those are targets. If you see you get to the end and you haven't met those targets exactly, that's okay. Those were just targets to get you started.
Okay.
Remember, you don't need targets. You don't need guides in the beginning. You could do this whole problem by just guessing at B and guessing at D until you get something to work.
Yeah.
And there's absolutely nothing wrong with that. You could just say, I'm going to go with B equal to 20, D equal to 40, and run through a couple of pages of calcs, find that it doesn't work, make adjustments, try again, run through the calc, find it doesn't work, but you're closer, make adjustments, do it again. There's nothing wrong with that technique. The guides that I'm giving you are trying to just cut down on the iterations, and they're trying to get everybody to the same answer.
I see.
Okay. But in real life, when I design a beam, I don't have anybody telling me that B should be equal to half a D or epsilon T should be greater than 0.075. That I'm just making that up for you.
Yeah, but you make assumptions as well in real life, right?
No.
You don't?
No, no. I have in real life, you have other constraints. Like the floor is 11'6" floor to floor. The architect has already determined that the floor is going to be 11'6". So I know I can't make my beams deeper than, say, 3 feet. Just making up numbers. But that would be something that I would know as an engineer, that the architecture has determined that I can't go deeper than 3 feet. So I'd start at 3 feet. and see if I can get it to work. And if it works super easy, then I might make it less than 3 feet. If it's working really hard, I might make the width a little bit wider to get all the steel that I need in there. See, but it's still in the real world, it's still kind of an iterative process.
Yeah. Okay. Thanks.
Yep. Okay. All right.
Yes.
Yes.
So Professor, the assumptions is just like it gives you range on like what specifications that you're gonna do, right?
It is really for the purposes of learning.
Okay.
It's really for these homework problems and maybe for a test problem so that you don't have to do, because I understand completely that none of you have the software that I have. I wouldn't expect you to have the software that I have. So it would take you much, much longer to go through multiple iterations than it would take me. And so it's really for the benefit of learning so that you don't go through, you'll still go through some iterations, but not like dozens of iterations. So it's to help guide you so that you don't have as many iterations, and it helps guide that all 23 of you on the call right now get to the same answer.
Okay.
Okay. What I was going to explain is if you all open your textbooks to page 598, Appendix A7, this rho factor here might seem to be coming out of nowhere, but it's not. If you look at your target of, well, first of all, look at 4,000 PSI is your second column, and grade 60 is your third group of rows down. And then you look at where epsilon t equals 0.075, that's rho equal to 0.138. That's where that number came from. So I didn't want you to look at this presentation and go, where did that come from? It came from that table using 4,000, grade 60, and epsilon t equal to 0.075. Everybody see where I got that?
Yep.
Okay.
Professor.
Yes.
So the only reason you see how epsilon sub t, you gave us this assumption, or because I know for the previous problems we have to find epsilon t.
Yes, and you're still going to have to find epsilon sub t. Yes, and thank you for your question. This is a target.
Okay.
This is just a guide to say we want to be around 0.075. What we actually end up with entirely depends on what I choose for the height of the beam, what I choose for the width of the beam, and what steel configuration I choose will determine what epsilon sub t really will be, but we're aiming for this 0.075 from the get-go.
Okay, I see. It's kind of like homework 1, problem 2. You know how the last one we have to find the width, but then we looked at the table, and if we're around the table, then that means we're in the right range, right?
That sounds right. I don't have problem 2 in front of me, but that sounds right.
Okay.
All right. So again, that we're not going to end up exactly with these numbers, and that's perfectly okay. We just needed something to kind of guide the answer. Because remember, without this, I could have a 10-foot deep beam, 12 inches wide. I could have a 3-foot beam, 2 feet wide, and they're all right. There's nothing wrong with the infinite number of solutions between. So we need something so that we all together, 22, well, 22 now, but they're back, 23, are all aiming at the same target. So with a target rho found, we need now to find a desired D value. Okay, so we use our reinforcement index, mu over phi BD squared. And I don't know B, I don't know D, so I can't use this, but I know that this is equal to this. And this I can use because I have a target row here, and I have Fy and F prime C. So if I plug in my target row, my grade, my target row, my grade, and my concrete, I get 0747 KSI, or 747 PSI. Now, what I can do is my mu over phi BD squared, I can substitute for B.
Professor,
Yes.
isn't it going to be 4 KSI?
Oh, you know what? You are the best at finding my typos.
But I made a mistake on my typos on homework too.
You are good. No, you are absolutely right. I said 4, I used 5. And I said 4 and I used that. Okay, let me just, for future generations, slide 326, 5 KSI. Okay, what was just pointed out to me for everybody else is that this right there, that 5 KSI is supposed to be 4 KSI, and I will fix it. But moving forward, because I can't fix it right now, moving forward, assuming that this is still the right answer, what I did here is I substituted B with D over 2. So that gives me 2 mu phi D cubed. And then I solve for D, and that gives me the third cubic root of 2 mu over phi Rn. I plug in my values, 2, 1500, 12 inches per foot. Phi is 0.9, 747. I get 37.69 inches. Therefore, the minimum D is 37.69 inches. So half of that is 18.85 inches for B. If I add 2.5 inches to my minimum height, 37.69 plus 2.5 gets me to 40.19 inch. That's awfully close. I'm going to try to go with 40 inches for my height. With a height of 40, then D is 40 minus 2.5 is 37.5. With D at 37.5, B is half of D. I rounded up to 20. So we're going to try to make this beam work 37.5 inches deep by 20 inches wide. With rho equal to 0.0138, D minimum at 37.69 and B minimum at 18.85, we can solve for our required steel. Again, the explanation to this is that many times you calculate the minimum here and here, that's the minimum. But then we choose something that many times is larger. D is about the same, but B is actually larger. So if I calculate how much steel I need based on what I chose, not based on what's required, I may overestimate how much steel I need. So that's why for the purposes of sizing steel, I use the minimums that I found. So,
Professor,
yes.
what was the reasoning why we substituted D over 2 for the width in the previous slide?
Because that was the problem statement. The problem statement was our target for the width
Oh, half. Okay, half. Yeah, okay.
was half a D. Yes.
Okay, thank you.
Okay.
That was the assume, right?
Yes, sir. Yes.
Okay.
Okay. So my required steel is my required rho times the minimum D, the minimum B. Again, if I put in my chosen D and my chosen B, those are bigger. So I would need more steel. I'm overestimating how much steel I need. because the math told me these minimums. I'm not going to use these, but I'm using them to find my minimum steel. Hopefully that reads clear. So this would tell me that my required steel is 9.8 inches squared. I choose 10 number 9s to satisfy 9.8. So 10 number 9s is 10 times 1 inch squared is 10 square inches per table 8.5. B minimum with 10 number 9s would be 25.57 inches. Table 8.5 is on page 597. I am assuming number 4s, unless somebody says otherwise, I'm assuming number 4s, I believe. And so with number 9s, this tells me I am 17.28 plus 2.26 times, I need 10, that's 6, so 4. That ain't right. Let's see, we got 10 number 9s. Yeah, what's going on here? Oh, a calculator. That's what happened. Plus 2.36 times 4. 26.72. Oh, I did use number 3s. Pardon me. I did assume number 3s. So again, everybody, I'm on page 597. I'm in table 8.5. I see that for number 3s, 6 number 9s is 16.53 plus add for each additional bar, the last column is 2.26 times 4. That gives me 25.57. That's where 25.57 came from. So whether you use the table or you add it up by hand, 25.57 inches is greater than my 20-inch width, so that's no good. I need to arrange my bars in 2 rows.
Professor, what is this number 3's U-shaped stirrups?
What, I'm sorry, what are they?
Yeah.
Those are your ties.
Okay. Okay. And then it included the reverb. Okay, it makes sense.
Okay, so when we talked about how wide a beam needs to be, we have the clear cover on the left, we have the distance from the outside of the tie to the center of the bar, we have the diameters of the bars, and we have the spaces in between the bars, and then we have the side cover on the right, and then the clear cover on the right. You add it all up. Well, if you assume number 3 ties, then DB is 3/8 of an inch. And then you add it up like we did. The table is just a shortcut. But you
Right.
need to know going into the table, are the ties number 3s or are the ties number 4s? And I made a statement a while ago, I believe, that if I don't tell you number 3s or number 4s, then go ahead and use the number 3s.
Okay.
Okay, did that answer your
So,
question?
Professor,
Yeah,
so when you use number 3, you use 6, which is 16.53, and then 4, 12.02. If we sum them, it's going to be 27.55.
No.
Isn't it?
well,
No,
there's,
at the very end, there's like for each additional bars.
yes.
Oh, 8, 8. Okay, got it, got it, got it. Thank you.
No problem. Okay, so just to reiterate, 6 number 9s with a number 3 is listed at 16.53, but we have 10 number 9s. So at the last column, it says for each additional bar, 2.26 inches
That's correct.
times 4 more bars gives you the 25.57.
Okay, okay, got it, got it.
Okay. All right, so we got a problem here. 10 number 9s does not fit in my assumed 20-inch width. Now we could provide a beam that's 26 inches wide, and then it would fit. But now we're way outside of our target of having the width being half of the depth. So I don't want to go that way because that takes me a long ways away from my target. So instead of making the width wider, what I can do is make the beam a little deeper and put my steel in 2 rows. Okay, so what we're going to do is, remember my minimum depth was 37.69. I typically add 2.5 inches to that to get to the center of the steel, but I'm going to add another 2 inches because I have to put that steel in 2 rows. So that means I'm going to take 37.69 plus 4.5 instead of 2.5 to account for those 2 rows. That gets me to 42.19. So I'm going to choose 42 inches. Okay, so even with our targets, there's still always going to be a little bit of iteration. This was a little iteration. I chose 40. I chose 10 number 9s. Oh, golly, it doesn't fit. All right, let's try 42 and 2 rows with 10 number 9s, and let's see if that works. So that's what we did. So then what I'm going to do is, with an H, a height of 42 inches, from that, I am going to subtract the 2.5 inches that is from the center of the lower row to the bottom of the beam. And then I'm going to subtract out 1/2 of the diameter of the bar. That gets me to the top of the steel in the lowest row, minus a 1/2 inch gets me to the center of the 2 rows. Okay. Maybe a little visual aid here. I am still assuming that the distance from the center of the steel to the bottom of the beam is 2.5 inches. That's right here. But then to get from the center of the steel to the top of the steel is D over 2, or 1.128 over 2. And then to get from the top of the steel to the center, the centroid of my steel, this space here is 1 inch. So I have to put in another 1/2 inch. Does that make sense?
Yes.
Okay, so that gives me a D equal to 38.44, because remember the goal, what are we actually after here? We're after the distance from the top of the beam to the centroid of all of my steel. So that's going to be 38.44 inches. Oh, look at that. I had a drawing all along. All right, so that's what I'm explaining. 38.44 is from the top of the beam to the center of all your steel. And here's my 10 number 9s arranged in 2 rows. All right, so now that we have chosen all these things, we have chosen the height of the beam, we've chosen the width of the beam, we've calculated the effective depth of the steel, and we've chosen what steel we're going to use, 10 number 9s. Now that we have chosen all these things, there are now no unknowns. So from this point forward, this becomes an analysis problem, not a design problem. So the first thing we're going to do, and this follows the format, this is consistent through all these designs, we're going to check the minimum steel. So the equation is 3 square root over Fy BWD, or 200 over Fy BWD. First one, and I'm back to 4,000 PSI concrete. So 3 times square root of 4,000 over 60, 20 times 3844 is 2.43. 200 over FYBWD gives me 2.56. 2.56 will control, but 10 square inches is well better than 2.56 inches, so we're fine with our minimum steel. You could, after a while, after you get comfortable with this, you can speed this up a little bit if you like by going to table 8.7. Table 8.7 for 4,000 PSI concrete and 60 grade steel, you will see that there's at the intersection of those two is row minimum for flexure 0033. Everybody see where I got that?
What table is it again, Professor?
8.7 on page 598.
And 4,000 and grade 60
4,000, grade 60.
and minimum flexure. Okay.
Yep. So that's 0033. So if I take 0033 times 20 times 38.44, what I get is 2.54, which is really close to 2.56. So if you like, after you've done this a few times, you can use that shortcut in the table instead of actually calculating both of these numbers every time, okay? But you should be very comfortable and familiar with where that number comes from.
So it doesn't matter if it's a little bit off.
No, nothing in concrete is really that precise. The reason that it's off is that the authors of the book reported the table to 0033 when it's really like 00332 or something like that. That's the slight discrepancy.
Okay.
Okay. Your homework one solution makes sense now.
Okay.
Okay.
The rounding factor.
Okay. Everybody okay? Any more questions?
Professor,
Yeah.
if we would check now with table A5, we would use 5 bars and not 10.
Yes, that's correct.
Okay.
That's right. So table A5, now your minimum width is 14.27, less than 20, so you're okay. Thank you for pointing that out.
So we don't do it because it's obvious, right? Kind of.
I'm sorry, one more time?
We don't do it, you didn't do it again because it's kind of obvious?
Yes, yes.
Okay.
Yeah, no, you're right. You're absolutely right. I didn't do it again because it's kind of obvious, but yeah, you're dead on. The table, you only have 5 in one row. So you would look up 5 for one row, 14.27, less than 20. So now we're good.
Okay.
Yeah, good comment.
All right, Professor, how do you check from table A5? I'm looking at table A5 right now.
All right, okay. Table A5, page 597. You see that the very top headers, you have number 3 U-shaped and number 4 U-shaped.
Yes.
Okay, we are assuming we are using number 3s because I didn't say anything about it. So if I don't say anything about it, assume number 3.
Okay.
So assume we're using number 3. Down on the first column, you see the rebars, number 4, number 5, number 6. Go to number 9. We're using number 9s.
Okay.
Okay, and then, so you got your finger on the number 9. Now, if you look at the screen, I've only have 5 number 9s in one row. So you move to the right until you get to the column headed by the 5,
Okay.
and you should see 14.27.
Okay, got it. So what does the 14.27 tell us from this problem?
The 14.27 is your minimum. So what that's saying is that if you were to try to build the beam narrower than 14.27, what would happen is the spaces between these rebars would be too tight and you wouldn't get adequate concrete flowing between the bars. That's what that means.
Got it. Thank you.
Sure, sure. And then a few of you have asked me, okay, well, if 14.27 is the minimum, what happens if I go to 20? Does the cover on the sides get bigger? What happens? The answer is no. The side cover remains constant. If that's 1.5 inches, it stays 1.5 inches. The side clearance due to the size of the rebar is constant. That doesn't change. So if you're wider than the minimum, then the only thing that happens is each one of these spaces between the rebars grows. Those spaces can be as big as you want them to be. They just can't be smaller than the code minimum. Okay, does that make sense?
Quick question. Making the space bigger between the rebars, does that strengthen the structure, or does that is it like a positive effect, or it doesn't really matter?
It's neutral. It's not a
Oh.
negative effect. It's not a positive effect, because the only thing that works in bending is your distance from your compression to your tension. So theoretically, you can make this beam 10 feet wide with 2 feet in between the bars, and it still has the same mechanical lever arm from the tension to the compression. So it doesn't change the capacity to spread them out or crunch them up. Doesn't change anything. But what does affect the structural performance is if these spaces are too tight, the concrete pours down from the top and gets hung up on them. And then you get this effect that's called segregation, where all of your rock clumps up on the bars and only the cement and water kind of bleed in through, and that's not good.
Okay.
Okay. And so 2.56 controls, 10 inches is bigger than 2.56, so we are plenty good for our minimum steel requirement. Now we're going to check our maximum steel requirement. And I had a few questions about this too, so we're going to take a minute to kind of revisit this. The first thing I want to say before we do the calc, whenever I say an ACI maximum steel check, what I'm really saying is epsilon sub t greater than 0.005? That's what I'm really asking. That's what the code really wants to know. Is epsilon sub t greater than or not greater than 0.005? Why is it called a maximum steel check? Because those two are absolutely proportional. The more steel you put in, the lower epsilon sub t goes. The less steel you put in, the higher epsilon t goes. The code isn't really concerned with how much steel there is. The code is concerned about where epsilon sub t is, the strain in that steel. Okay, so anytime you see maximum steel check, that's code language for what is the condition of epsilon sub t. Okay, so let's calculate epsilon sub t. We need to find A. A is ASFY over 0.85 F prime CB. I plug in my values. I get 8.82 inches. Beta 1 is 0.85. I grabbed that from the table. So C is A over beta 1, which is 10.38 inches. So epsilon sub t is 0.003, D minus C over C. And I get 38.44 is my D, minus 10.38 over 10.38. And I get 0.0811. That is greater than 0.005. So we are okay. and your phi factor can be taken to be 0.90. Okay, so this is the check. This is what matters right here. Epsilon sub t, is it or is it not greater than 0.005? Now, having said all that, we have a table, table A.7 on page 598. So if you go into that table with F prime C equal to 4,000 and grade 60, you see that we have this thing called row balanced, row when epsilon t equals 0.004, 0.005, 0.075, and then minimum. Everybody see where I've got my finger?
Yeah.
Okay, so the one that matters, the one that you're concerned about is row when epsilon sub t equals 0.005. Remember what I just said. All the code cares about is epsilon t greater or less than 0.005. So we have, I'm sorry? Okay, so we have an entry here for 4,000 PSI, grade 60, row when epsilon t equals 0.005. That number is 0.0181. What does that mean? That is a row value. So row is always the area of steel over the area of concrete. And that value of 0.0181 represents the maximum steel you can put into this beam. So instead of doing this, you can go to that table and see that it says 0.0181. Then you can take 0.0181 times B equal 20 times D equals 38.44. And that gives you an area of steel of 13.92 inches squared. What does that mean? 13.92 inches squared is your maximum allowable steel, because that's the area of steel in this beam that would give you epsilon t equal to 0.005. So as long as the steel that you choose, not your calculated requirement, but the steel that you actually choose to put into the beam, as long as that steel is less than 13.92, which in my case, I'm providing 10, then when you calculate epsilon sub t, it will be higher than 0.005. So the table is a shortcut, an indirect shortcut to get you to check epsilon sub t. And you can use that table, or you can just calculate epsilon sub t. Until you get comfortable with these concepts, until this is like the back of your hand, I suggest you just calculate epsilon sub t. That is what the code is looking for. That is a direct check to what the code is asking. But you could use the table and make sure that the steel you provide is less than that value. And what that means is when you check epsilon sub t, it will be okay because you're under that threshold. Does that make sense? To anybody?
So, Professor, you compare the area of the maximum steel to the required,
No, to the chosen.
to the which in our case is 10 inches, right?
Right. The required was 9.8, but I'm providing 10. And
So
that's
if it's greater than your epsilon is greater than as well.
Right,
Okay.
right. Or, well, the opposite. If you provide more steel than that maximum, then your epsilon sub t is going to be smaller than 0.005.
Oh, so your chosen area should be less than the maximum steel.
Yes,
Okay, yeah.
but more than the required steel.
Right. Okay.
Okay. All right. Let's finish out this problem, then we'll take a little break.
Oh, one more, Professor. Did you assume the beta is 0.85 as well?
Yeah, right there.
So do we just like assume it's always 0.85 or?
No, 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 no. Look, table 8.7, you got to go to the
Oh,
table.
it depends on the PSI as well. Okay, that makes sense.
Yeah, depends on the PSI of the concrete.
Yep. Okay, thank you.
Okay. All right. Last step. Again, you will be tempted that the required steel, you have provided more steel than the required steel and less steel than the maximum steel, so everything's good. But no, you have to do this last recheck to make sure that you have your capacity. So I'm going to check that my 10 square inches of steel, 60 grade at 38.44 D minus ASFY over 1.7 F prime CB equals 18,375 kip inch, 1,531 kip feet. And this is where you get paid. This is the money-making calc line. VMN equals 1531 is in fact greater than 1500. Therefore, the design is acceptable. Okay. Any more questions on last lecture? Okay, that's the end of last lecture. So let's see if I can work the technology here. That's lecture 5. And we go to the top. Okay, can everybody see lecture 5?
Yes.
Okay, perfect. Thank you. All right, it's 5:53. Let's meet back at 6:05. Let's make it 6:05 tonight. And so I'll see you in a few.
All right.
Is that MATLAB?
It is.
Oh. Professor, I have a question. So when you say that you find the minimum and maximum steel, it's a check. It's you're not looking for the what is the maximum steel and what is the minimum steel, right?
It's a check, yes.
Okay,
It's
so because well, I just know this one in the homework. I thought you were just asking what is the maximum steel and then what is the minimum steel requirements. So I didn't know that we need to check the epsilon t and compare it.
yeah, that's what's meant by the maximum
Okay.
steel. The minimum steel are those two equations that come
Yeah.
right out of ACI, and you have to provide at least that much steel. But the maximum steel is not a simple equation. The maximum steel is checked by finding what epsilon sub t is. And remember, it's an inverse proportion. So as long as epsilon t is bigger than 0.005, then your steel is smaller than the maximum steel.
You're right.
Okay. But that's going to be common, like every design and analysis problem we do for flexure. And when I think we got 1 or 2 more lectures on flexure, every problem we do for flexure will have, you design it, you choose your depth, you choose your steel, you make these assumptions, and then you check minimum steel, you check maximum steel by checking epsilon sub t, and you always check that your allowable strength is greater than the demand. Those are like the 3 things you always do.
So like the way I see it is like you have a range of minimum and maximum, and if you're in the middle, it's good, but you still need to check the demand.
Correct.
Okay.
Yes, correct. Now, if you need more steel than the maximum allowable steel in order to meet the demand, then you got a problem. You need to make the beam deeper or change something, make the load less, make the beam deeper, but
And
you can't
dimension.
just keep piling in more steel.
Got it. Thank you.
Okay. All right, everybody. We are back and we are here to talk about one-way slabs. Okay, so what is a one-way slab? A one-way slab is typically a flooring system that is cast in and spans between 2 beams. So you can see I got a beam here, I got a beam here. This is just a cutout, right, of some typical concrete flooring system. And the concrete, it's all monolithic, notice. See, the beams and the floor slab is all the same pour of concrete, but the thinner section spanning from beam to beam we call a one-way slab, and then the beam sections themselves are the beams spanning probably from column to column, okay? So, like I said, one-way slabs are usually monolithically poured with their supporting beams. This is all one big blob of concrete. But the one-way slab is what we call the thinner slab that is spanning from the beam to the beam. Due to support geometry, one-way slabs span from one way from support to support. To be looked at later, there's such a thing called a two-way slab, which actually, if you have beams on all 4 sides, then the concrete is spanning in both directions at the same time. That's a bit more complicated, but one-way slabs are pretty simple. To design these, if you want to think about it this way, we can take a section of this slab and isolate it for design purposes. So we can look at only for a defined width of the slab, like so. And then we can design it as if we cut it out of the whole system and we just designed this little strip. So if we cut out a strip for design, what we now have is a shallow, wide, singly reinforced rectangular beam. Again, we've taken something that is somewhat complicated, reduced it to something more simple. So if I look at the side, at a side elevation, so here's the two beams that you saw in the isometric, and this is the slab spanning between those two beams. So in a side elevation, what we call the clear span is labeled as L sub n. And I used a script, lowercase script, because ACI 318.652 still uses a lowercase script for L sub n. L sub n is known as clear span. So that's the distance from the inside face of the girder to the inside face of the girder that is spanned with this slab. If I take a section of this slab for design purposes, the slab has a height of h or a thickness of h, and for convenience, no other reason, just for convenience, we're going to look at a 12-inch wide section of this strip. So this becomes my design beam. My beam is a height of h and a width of 12 inches. Our assumed beam section is 12 inches wide by h deep, rectangular, singly reinforced beam. Okay, loading. So typically for a floor system in a concrete building, not always, but many times the loading is defined as W sub U, which is a uniform loading. ACI 318 section 6.5 provides simplified method for finding moments and shears and one-way slabs, provided that you meet these guidelines. Okay, so what am I talking about? Well, let's back up a little bit. What am I talking about? If the loading on this one-way slab system is a uniform load, so it's say 120 pounds a square foot dead load and 40 pounds a square foot live load, something like that. That's a uniform load. It's given to us in pounds or kips per square foot. So with the uniform load, if you have a deck system that may have, I'm only showing you the end bay, but it may have multiple bays, beams on regular centers. You could have 4, 6, 20, 30 bays in your building. And if you remember from your structures class, if you have a flexural system that is supported in several places, what you have is a continuous span system. And what that does is it generates positive moments in the middle of the span, negative moments over the support. And how did you solve for these? How did you get the positive moments and the negative moments for a multi-span structure? Anybody remember? Anybody take structures?
Is it, do we have to use the point loads and stuff like that?
Not point loads, but somebody should have taught you at least one of several techniques for solving for indeterminate structures, right?
Energy method.
What is that?
Energy method.
Energy was one of them.
Virtual load.
Moment area was one.
Moment area and virtual work.
Virtual work, yes.
And then the formula.
Moment distribution.
And
So the ones I remember are the energy method, moment distribution, moment area, and the stiffness matrix method.
stiffness, is that the influence line?
No, no, no. Stiffness, where you have to generate your stiffness matrices and then generate loading matrices and restraints. And then you do matrix operations to get global deformations, then local deformations, all that good stuff.
Oh, wait.
Yeah, I don't think we did that.
Yeah, I know
What?
the energy method and maybe the virtual. We have the virtual work as well,
Yeah.
and then we use the formula.
Okay. Moment distribution,
E
where you had all the little boxes and you go through iterations until you get to convergence. Okay, well,
I don't remember.
all right. Okay. Well, anyway, at least you have an idea that this is a complex problem. That's really what I'm trying to get to. Whichever method you use to solve these, it's a fairly complex problem. And in real life, rarely do we do them by hand anymore. We have software, finite element, or frame programs that will solve it for us. But it's a fairly complex problem that you need advanced software to solve. The point is, if you meet these guidelines that I'm about to give you, then ACI has a method that you can use that will give you the moments and the shears without going through those techniques to calculate them yourself. If you do not meet these guidelines that I'm about to give you, then you do have to create a frame model or a finite element model or go through moment distribution or one of those methods to calculate what your moments and shears are at various places in this structure. Okay, but if you fall within this broad category, which captures like 85% of the structures out there, then you're in luck. The code tells you what to use instead of having to calculate it yourself. So what are these guidelines? First of all, that the members are prismatic. So all that means is the beams have the same section from end to end. And the one-way slab here, if it's 6 inches thick, it's uniformly 6 inches thick. It doesn't vary from end to end or what have you. So if the members are prismatic, if the loads are uniformly distributed, like I show here, where the loads are W sub U, they're in PSF, then you're in luck. If you got big old point loads, like from heavy pieces of equipment or traffic or trucks or something like that, you're out of luck. You got to figure out what you have. If the live load is less than or equal to 3 times the dead load, then you're in luck. You can still use this. And that's pretty lenient because if you have 100 pounds a square foot dead load, then as long as you don't have more than 300 pounds per square foot live load, we're okay with this method. There has to be at least 2 spans, right? What I'm showing in the illustration is 1 plus something going over here. So that would be 2 spans. You have to have at least 2 spans for these things to distribute. The longer of 2 adjacent spans does not exceed the shorter by more than 20%. So the spacing from beam to beam to beam to beam doesn't have to be perfectly the same, but it can't vary by more than 20% from span to span. If you meet all these conditions, then we can use ACI 318 and we have some span tables 6.52. If you have a beam that is simply supported, then your maximum moment is WU L sub n squared over 8, which is kind of duh because everybody knows that simply supported beams, the moment is WL squared over 8. So that's a gimme. And that would be your maximum possible moment in the middle of your span. If you're simply supported, you don't have any negative moments by definition. Okay, so now if you have an end span like the one I show here, because this is the end or the edge of the structure, then the discontinuous end integral with the support, you have a moment of WL squared over 14. And that is again in the positive region at the midspan of the end bay, if you will. So it's the middle of the end span. If you have a discontinuous end that is unrestrained, so the one that I showed here, the slab pours into a beam, that would be integral with the support. If the slab just kind of stopped and there was no beam there at all, then you would have ML squared over 11. Would be your maximum positive moment. If you have interior spans, so this span and all the rest of the spans in the middle, then your maximum positive moment is WL squared over 16, which is in the middle of that next bay. So far, so good?
Yeah.
This is in the formula table for the moment, right? You just change. You're just explaining what's the X and Y and the load as well.
It's, I'm sorry, where?
Like, I think I remember some of these is in the formula, so finding the moment, and then you just basically like explaining which one is X, which one is the live load, dead load as well, right?
No, that this should be, if I'm understanding your question correctly, this should be completely new material. This is coming straight out of the code. And it's a design guide so that you don't have to calculate all this by advanced techniques.
Okay.
So this is not something that we've covered before or that you've seen before. And you probably have not seen this in your theory classes because the theory classes are not material specific, but these values are only for a concrete slab.
Professor, for these, do we ever take count the maximum shear? Like say like in the middle of the slab, maximum shear would be 0, right?
Yes, but we'll hit the shear in just a sec.
Okay.
Okay, well, what we talked about so far was just positive moment. So positive moment is in the middle of the bay. Positive moment causes cracking at the bottom and crushing at the top. That's the definition of positive moment. Now we're going to look at negative moments. So negative moments cause cracking at the top of the slab and concrete crushing at the bottom of the slab. It's the opposite. And you get your negative moments typically over your supports. So negative moment, and you have to be careful about where you're looking at. These are very specific. So the interior face of the exterior support. And if the member is built integrally with a supporting spandrel beam, like I show here, then your moment will be WL squared over 24, which is right there. That's where you experience the worst negative moment in this location. If the member is built integrally with supporting column, which I'm not showing here, then you have WL squared over 16, which would be in the same location. The exterior face of the first interior support is here. If you have two spans, you have WL squared over 9. And it's right there, that's where that moment exists. And if you have more than two spans, you have WL squared over 10, same place. And at the face of all other supports, not specifically here or here, then your moment's going to be WL squared over 11, as shown here. Okay, so again, this is just generalizations that the code gives us in very common applications so that we don't have to go through the work of building models and doing the structural analysis. The face of all supports satisfying A or B. Let's see, slabs with spans not exceeding 10 feet. You have WL squared over 12, and beams where the ratio of sum of column stiffness to beam stiffness exceeds 8 at the end of each span. It's getting a little convoluted, but that's WL squared over 12 as well. And I did not show where those are. Okay, so face of all supports satisfying. Okay, so I think what this is basically saying is that here's a couple of special categories where if you meet these requirements, then you get a little bit of a break. WL squared over 12 is better than over 9, 10, or 11. See, so if you're getting into a little bit of trouble with these moments, if you meet these criteria, you can back off a little bit. A little advanced, don't really need to dwell on it, I guess. Shear, so that's positive moment. This is negative moment. Now for shear, the exterior face of the first interior support, your shear is taken to be 1.15 WL over 2. That is here. This is your exterior face of the first interior support. The face of all other supports is WL over 2. And that would be here and everywhere else. Okay, so let's see, ACI 318, section 7311, table 7311, provides a simplified guide for the minimum thickness H of one-way slabs. So again, we're designing this continuous system as if it was a beam H high, 12 wide. So to get you into the ballpark of how high does H want to be, you follow this table. And the table, I'm basically just reproducing the table for you. If the one-way slab is simply supported, it's on rollers at both ends, then H should be greater than or equal to the clear span L sub n divided by 20. So now you got to watch your units on this. If the clear span is, say, 15 feet, then 15 divided by 20 gives you 0.75. But that means H needs to be 0.75 feet. If I take 15 times 12, so if I take my clear span to be 180 inches, then 180 inches divided by 20 is 9 inches. And of course, 0.75 feet is 9 inches. So it always works, but just be careful of your units. If you plug in L sub n is 15 feet and get 0.75, that does not mean that the slab has to be at least 0.75 inches. The units are whatever units you used for your clear span.
Professor, is the
Yeah.
table for this in the book? I'm trying to find it right now.
I don't know. Good question. Let's see. Where in the book does it talk about slabs?
It says chapter 4, one-way slabs.
Yeah. Oh, there you are. Page 98. Okay. One-way slabs. Oh, you know what? I think what they did, I think I ran into this before. I think it is all in here, but they don't reproduce it in a table. It's all in text, paragraph text. Oh, wait, see table 4.1. Where the heck is table 4.1? Okay, here's a mystery. Can anybody find table 4.1? one-way slabs, figure 4.7. Did they forget the table? I'm looking on page 100.
I think they just refer to the code book. It keeps saying ACI code.
Yeah, but I'm wondering if, well, it's the same table for beams, so maybe they presented the table earlier on. Okay, page 84. Table 4.1 on page 84. That's the table that I'm talking about right now. And they presented it on page 84 because it's the same table that you use for beams. Beams and one-way slabs share the same table, so they presented it earlier in the book. That's where you look, page 84.
Thank you.
Sure. All right, so back to this. If one end is continuous, see what I've got drawn here, both ends are continuous. But if one end only was continuous and the other end was on a roller or simply supported, then your minimum height is Ln over 24. If both ends are continuous as drawn, then Ln over 28. If you have a cantilever, picture like a balcony where the concrete slab cantilevers off the building, yeah, that's pretty tough. So you gotta make sure you have Ln over 10 in that case. ACI 318-73111 prescribes for Fy other than 60,000 PSI, modify the above by okay. So what this is saying is all of these are based on Fy 60,000. If you are using steel that is less or more than 60 KSI, then use this equation here to multiply these values. ACI 73112 prescribes for lightweight concrete to modify the above, these guys here, by the larger of A or B. And so A is 1.65 minus 0.005 times the density of your lightweight concrete, or multiply all of these by just 9%, 1.09. Because, why do they do that? Because lightweight concrete has more deflection than does normal weight concrete. So they're compensating. Similar to beams, one-way slabs do have an absolute minimum strain, epsilon sub t equal to 0.04 with the fee penalty. Oh, and I didn't type it in there, or 0.05 with no penalty. So the whole strain condition applies to one-way slabs, just the same as beams. Minimum temperature and shrinkage reinforcement. Okay, so this is a little different. You don't see this for beams. What happens in slabs is that, actually, let me go back to a picture. Not to backtrack too far here, but there. When you build a deck, a concrete floor, you typically have beams in one way, the slabs going the other way. And once you have poured this and it starts to cure, concrete shrinks. We talked about this in lecture number 1. Concrete will shrink. So the beams are basically restraining this slab from shrinking. It has nowhere to go. It's being restrained by beams and columns. So that means it's going to crack. And that's okay. All concrete slabs crack. But you need to be sure that you have a minimum amount of steel in there so that when the slab does crack, it doesn't crack horribly. It's kind of, well, it really is more of an aesthetic situation than structural, unless it cracks really, really bad. But typically, in a concrete slab, due to shrinkage, it will crack. And as long as you have a minimum amount of steel in there in both directions, then the cracks will be controlled by that steel. Okay. And then temperature, of course, also, if you have a concrete slab that is subject to temperature differentials, it can go up, it can go down. Then when the concrete cools down, it contracts, and that too produces tensile stresses that you need to control with temperature and shrinkage reinforcement. So these effects are much more profound in a thin slab than in beams that are spanning from one end to the other. So the requirements for the steel, minimum steel for one-way slabs is different than for beams. So ACI 318.764 points to section 24.4, table 24.432, which gives you the minimum ratios of reinforcement to the gross concrete area. Okay, now here's the key. I'll give you the first number. If you're using deformed bars with a yield less than 60 KSI, your minimum reinforcement ratio is 0.02. But I want to be clear about something. This is missed almost every time. This value is not rho. This is not a rho value. Rho is the area of steel over BD. This is the ratio of reinforcement to the gross concrete area. It's a slight difference, but a big difference. Gross concrete area is the assumed width times the thickness of the slab. Rho is the width times the distance to the centroid of the steel. Those are two different things. So this ratio here is not compared to BD. It is compared to BH. Everybody clear about that? It's simple, but it's easy to miss.
Kind of clear, Professor.
Kind of clear? I'm sorry, was there another question?
No, it wasn't a question. I'm just it's slow to process, but I'm getting it.
Okay, 10-4.
So it's like the gross concrete area is always bigger than the row per se.
Absolutely, yes.
Okay.
So H is the thickness, right?
H is the overall thickness of the slab.
Okay.
Okay. Deformed bars or welded wire mesh. And this category is where Fy is not less than 60 KSI. So we have one of these greater ofs, right? So if you have grade 60 rebar or you have a welded wire mesh, then you need to provide 0.018 times 60 over Fy or 0.014 as a minimum. Whichever of these two is greater, that's the reinforcement ratio that you need to check against. Okay, so it's either this for grades less than 60 or the greater of these two for grades of 60 or greater or anything welded wire mesh. And again, these ratios are multiplied times B times H. Now we also have a maximum spacing. We don't have this in beams because the spacing of the rebar in a beam is pretty much dictated by the width of the beam that you provide. But in a one-way slab, the width of the slab could be 30, 50, 100 feet wide. It could be as wide as the building, right? So we need to have a prescribed maximum spacing of our reinforcement. ACI 24433 gives us that. And it is the lesser of 5 times the thickness of the slab or 18 inches. So we can never space our rebar in either direction more than 18 inches or 5 times the thickness of the slab, whichever is least. ACI 318.7711 points to section 20.61 for your minimum coverage requirements. ACI table 26131 gives the minimum coverage for reinforcement. Now this is for corrosion protection. ACI does not give us values for fire protection because that comes from a different source. But for corrosion protection, we go to this table 26131. If your slab is exposed to weather or in contact with the ground, then all members with number 6 through number 18 bars need 2 inches of coverage. And when I say coverage, let me draw you a little picture here. Say like this is my slab. There's my rebar. The coverage requirement is from the bottom of the bar to the nearest exposed face. That's what's known as coverage. It's not to the middle of the bar, it's to the bottom of the bar. And don't forget, in one-way slabs, we have reinforcement going in both directions. So I'm showing reinforcement coming in and out of the page, and I'm showing reinforcement going left and right on the page. And sometimes, well, as a designer, you don't know, is this the bottom or the top? Is this bar on top of that bar, or is that bar on top of this bar? We don't know that. We can try to specify that. Well, in one-way slabs, I take it back, we do specify that. So in one-way slabs, the bars that are going parallel with the span should be put on the bottom because they're the most important. And the bars that are going transverse or perpendicular to the direction of the span go on top of them because they're there just for temperature and shrinkage. They are not there to resist any kind of load. Okay.
Professor,
Yes.
I have a question.
Yeah.
For the spacing of the bars, is both directions have to be spaced the same or?
No.
Okay.
No. But both directions need to be less than the maximum. But usually one direction will be a different spacing than the other.
Okay.
Okay.
Yeah, 'cause from what I see from the picture from the slab, one way is longer than the other, right?
It is.
Okay.
But in a one-way slab, we're assuming in one direction, it's resisting load. So say like your span is from east to west.
Okay.
Okay. So your support is on the east side, the other support's on the west side. So the rebar supporting the load is going east to west. It's going parallel with the span. And that would be this green bar here. And you would size those bars for your flexural demand. But you also need to put steel in there going north to south. The steel going from north to south is not by design supporting any load at all, but it still needs to be in there for temperature and shrinkage. So what you would see very commonly, the green bars going parallel with the span may be number 6s at 12. The red bars that are not supporting any load, but just are there for temperature and shrinkage, those may be number 4s at 18.
Got it.
Okay, so back to the coverage. The coverage is measured from the bottom of the bar to the bottom of the slab. And for weather or ground, you need at least 2 inches because these are nasty. For a number 5 bar, a wire 31 or a deformed wire 31 or smaller, you need 1.5 inches. If your slab is not exposed to weather and is not in contact with the ground, this gets a lot better. For slabs, joists, and walls, which we're talking about slabs, for number 14 and 18, which you would never see in a slab, but you would need 1.5 inches. For a number 11 or smaller, which you do see in slabs, you need 3/4 inch. So typically this is about 3/4 of an inch for most applications. Typical one-way slab.
I have a question, Professor.
Sure.
So you mentioned that when the slab is touching the ground, does that mean your beam is underground or something?
It could. That's not a common situation because, and I'll make a distinction because I can imagine this would be really confusing. If you pour concrete directly on the ground, we call that a slab on grade. And that's actually a foundation system. It's not a one-way slab. Because when you pour the concrete directly on the ground, then the concrete is directly supported by the ground. It's not spanning from beam to beam. It's just being supported by the dirt. And this would be like your driveway, like a sidewalk, like if you have a garage with a concrete floor in your garage, that's what we're talking about. That's a slab on grade. That's not a one-way slab. And very interestingly, slab on grades are not covered by ACI 318. They do not deal with slab on grades. Those are foundation systems, not structural systems. Very interesting. But there is a way that you could have a one-way slab that is exposed to the ground. There's various ways that this could happen. One way could be that you pile up dirt on top of it. You're storing dirt. Well, that's just as bad as being touching the ground, right? In terms of the chemical reaction between the materials. There's other ways you could have a retaining wall system where maybe your slab is vertical, not horizontal, and it's spanning. It's more like a wall, but it's spanning. That would qualify as in contact with the ground. And there's some other ways, but typically slabs, one-way slabs are not in contact with the ground typically. They could be in contact with weather. You could have an open parking garage. That would be a slab exposed to the weather. But like I said, this 3/4 inch here, that's really more of your typical situation.
Okay, makes sense.
Okay. If you have beams, columns, pedestals, tension ties, and we're talking about the primary reinforcement, stirrups, ties, spirals, and hoops, then you need 1.5 inch cover. And by the way, we're just discussing beams, and I said that side cover is usually 1.5 inches. Here's why. That's where it says that it should be 1.5 inches. Okay. Let's do an example. Here, I've got a concrete slab system spanning between 2 beams. The clear span is 12 feet. What we're given is 3,000 PSI concrete and 60 KSI reinforcement. We are giving some weights. The dead load of the slab is 100 pounds per square foot, but that does not include the self weight of the concrete itself. The live load is 100 PSF. The slab has more than 2 spans. Solution. According to ACI table 7311, both ends are continuous, as you can see. So our minimum thickness should be LN over 28, which is 12 feet times 12 inches per foot over 28 gives me 5.14 inches minimum. So I'm going to choose a 5.5 inch slab. For my loading, my slab is 5.5 inches by 12 inches, and I got 3/4 inch cover as we just discussed. So now, as you can see, this is a beam problem. We just took it from a slab problem to now I'm designing a shallow, wide beam. So for my dead load, I have my 100 PSF as given, plus I have 5.5 over 12 times 150 pounds per cubic foot to account for the weight of the concrete itself. That gives me total 169 pounds per square foot for dead load. Live load was given at 100 pounds per square foot. We need to check our different load cases. I can have 1.4 times the dead load is 237 pounds a square foot, or I can have 1.2 times the dead load plus 1.6 times live load. That's 363 pounds per square foot. In this particular problem, I did not give you an SDS factor, so you can assume that the third equation with the SDS in it does not apply. So in lieu of the third one, the greater of the two is a 363. We're going to design to 363. For our positive moment at the middle of the span, it's an end span. It's a discontinuous end integral with a support. So we're going to use mu equal to WL squared over 14. So WU is the 363 times 12 squared over 14 gives me 3.73 kip feet. Typically with these problems with one-way slabs, it's more appropriate and useful to use kip inches. So we're going to convert that to 44.8 kip inches. That's my maximum positive moment. My negative moment,
Professor,
yeah,
the positive moment, is that usually in the middle?
it's at the middle of the slab between the beams.
But it's not exactly in the middle, right?
You can take it as midspan, yes.
Okay.
Yeah, you can. It doesn't really matter because you're not analyzing it. And whatever you come up with, you're going to take that rebar and spread it out a bit. So it's not precise, but it is assumed to be the maximum positive moment is at the midpoint between two supports.
Right. Okay.
Professor, and for this problem, the loading on top of the slab, we ignore it?
We didn't ignore it. What do you mean?
That's the WU.
Well, let's go back here. That was a serious acquisition.
Sorry, it's because I'm looking at the picture, not the bottom right picture. Oh, okay. I see.
Okay, yeah, I want to make sure they were clear about that. I ain't forgetting no loading anywhere.
Okay.
That's what all of this was.
Yeah. I was just looking at the picture itself.
This is just a section. This is the loading diagram.
That's the cut, right? That you do.
Yes, that's it. This is a cut. Like if I cut right in here and I look in there, that's what I'm looking at.
Oh, gotcha.
And Professor, the weight of the concrete is 150?
It is assumed to be 150 unless I tell you otherwise. There is lightweight concrete out there that could be 115, 125, but if I don't tell you anything, you just assume 150 for hard rock normal weight concrete.
That's the unit weight of concrete, right?
Yes.
Okay.
Okay. The negative moment. Negative moments found at the interior face of the exterior support. Member built integrally with the supporting spandrel beam. We are going to use WL squared over 24. At the exterior face of the first interior support with more than 2 spans, we're going to use WL squared over 10. Of the two, I'm just going to use one rebar configuration. So I'm not going to design one and then design the other. I'm just going to take the worst of the two, which is the WL squared over 10 is the one that's going to control in this case. This is a engineering judgment. There's nothing wrong with designing this location for over 24 and these locations for over 10. Nothing wrong with that, but I'm choosing for simplicity to take the worst one.
Professor, I have a question.
Yeah.
For the, how do you, because I'm looking at the table from the book and it says one end continuous and both ends continuous.
Which table in the book are you looking at?
I'm looking at the one table 4.1.
Okay, but we're doing something different here.
Oh, okay. I'm sorry.
No, I mean, there's nothing wrong. It's just that that table is what we used to decide how thick the slab should be. That's
Okay.
how we got to a 5.5 inch thick slab.
Right.
But that table does not tell you anything about what moment to design to.
Got it.
So these are the tables that we're using to come up with the moment. Otherwise, we'd have to do this big old full-blown analysis to come up with the moment. I'm going to use the ACI simplistic equations to come up with the moment. So the table you're referring to is the design guide to get you to a thickness of slab, which we need to get the dead load, which we need to get the factor load, which we need to get the moments. But now we're on to getting moments.
Moments. Gotcha. Got it.
Okay. So I'm using this one as my worst case. So my load of 363 times 12 squared over 10 gives me 5.23 kip feet, gives me 62.7 kip inches. This is my design negative moment, and the previous page was my design positive moment. Okay, so now I'm going to go back to my positive moment region design. I assume I'm going to use number 5 reinforcement. Again, there's a iterative process to this. I could use number 4s, I could use number 6s. I'm choosing number 5s. And so a number 5 has a 0.31 inch squared area and a 5/8 inch diameter. With number 5, my effective D is going to be 5.5 minus my 3/4 inch cover minus my bar size diameter divided by 2. Now, here, hopefully, again, trying not to confuse everybody. The beams that we just did, we said D is H minus 2.5, and that's a good number to use to get to D for beams. But this is different. Beams have 1.5 inch cover, and they have the thickness of a tie that goes underneath those bars. These do not have ties. There are no ties in a one-way slab. So there's no ties to figure into this. The cover is half the cover of a beam. And most importantly, you're only working with 5.5 inches in the first place instead of 20, 30, 40 inches. So a little change in the D is much more profound on a one-way slab than in a beam. So whereas in a beam, it was okay to just assume 2.5 inches, and that got us close enough. That is not close enough for a one-way slab. One-way slabs, we actually calculate what D is. D is the thickness of the slab minus the coverage minus half of your bar. And I get to 4.44 inches. I use my RN factor, mu over BD squared. In this case, I know everything. I know my moment. I know my B is always going to be 12 for a one-way slab. And my D I just calculated is 4.44. So I get 210 PSI. From the table, I can find it quicker from the table. So my rho required is 0037, which is greater than 0033, which is your minimum rho. and it is less than 0.136 from table A7, that corresponds to epsilon sub t, okay? So I'm already utilizing that shortcut that I talked about earlier at the beginning of this lecture. So I am going to assume then that I have just made my two checks. I just checked my minimum steal and I just checked my maximum steal right here with these two line items. So if I use 0037 times my width times my D, I get 1.97 inches squared. So now we're going to find the required spacing for a number 5 rebar. I know we're getting to the end here, but this is important. Please catch what I'm doing here. The spacing, and we don't do this for beams, so this is brand new. The spacing that is required of your rebar is equal to the area of the bar divided by the area that is required times this 12 inches per foot thing. And so if I put in the area of my rebar, 0.31, over the area that is required, because the area that is required is actually per foot. So then you multiply times 12, and that cancels out that per foot thing. And what you're left with, this mathematically, 0.31 over 1.197 times 12 is 18.88. That is your minimum spacing. If you put a spacing larger than this, you don't have enough steel. You put a spacing smaller than this, you're fine. So that's my maximum spacing. But ACI 24433 prescribes maximum spacing of the deformed reinforcement as the lesser of 5 times the slab thickness, or, well, 5 times 5.5 is 27.5 inches, or 18 inches. 18.88 is more than 18 inches, so I got to put my spacing at 18 inches. So for positive reinforcement, we're going to put number 5s at 18 inches on center. The area that I'm providing then is equal to the area of the bar times 12 over your spacing. So 0.31 times 12 over 18 is 0.207 inches squared. This is technically 0.207 inches squared per foot of slab. Now I got to do my strength check. This is my area of steel, like I said, and be careful about this. I really want to emphasize, you got to get home these two concepts. You can't just put in 0.31 because you're using a number 5 bar, because this check is per, right there, 12 inches of slab. So you got to put in how much steel you're providing per 12 inches of slab. So there's your 207, 60 grade, D, 207, 60 grade, 3 KSI on the slab, 12 inches wide. I get a capacity, allowable capacity of 47.4 kip inch, which is greater than 44.8. Therefore, my design is adequate. Okay, that's the positive moment region. We will pick this up next week on Tuesday. We will pick this example up on the negative region. We are slide 195 out of 232, so we got a little ways to go. Does anybody have any final questions they'd like to ask me before the weekend?
Professor, I have a question about the homework.
Sure.
Is there any way we can have it due on Thursday so we'll be able to have like an office hours? Because I know if it's due on Tuesday, we won't have like an office hour.
You do have an office hour on Tuesday.
Oh, that's right. Before class. Right.
Before class.
Yeah,
So
because
you-
it's at 12. It's due at 12.
That's right. You have an office hour before class. You have the entire class to ask any question you could possibly imagine. And then you still have 5 hours to do it afterwards.
I have a question on the spacing, Professor.
Okay,
Can you go back a little bit?
sure.
Slide. So we're basically comparing the 18.88 to 27.5 and 18, right?
Yes,
And the lesser off is that like which one of the three is less?
yes,
Okay.
yes, yes. This is one of those things where the lesser spacing is more steel. The more you space it out, the less steel you're providing.
Right. And then oh, so does that means since the only thing that we're testing is 12 inches width, does that mean like uh there's like a 12 inches width of the slab that doesn't have steels in it, and then
No,
there's this
no, it's not like that because every time we're doing this design, we're really designing something that's 20, 30, 50 feet wide. So,
okay.
so we're only taking a 12-inch wide strip for design so that everything is really nice and easy. All of our moments are actually per foot. My compression element down here is 12 inches. It makes everything simple if we just design a 12-inch strip. But we never are designing a 12-inch strip. It's always something 10, 20, 30, 40 feet wide. So when you put your rebar in at 18 inches on center, it averages 0.207 per foot, but it's really many, many pieces of rebar spread out at 18 inches on center.
Right. Okay, that makes sense. I guess you answered my question. I was gonna ask you earlier if there's like a U in the slabs, and you mentioned it. There's none.
Typically there is not, correct.
The U tie. Okay.
Right.
Okay. Thank you so much.
You're welcome.
Professor, can you explain again why the 18 inches controls?
It's the least. The code says you cannot space your rebar more than 5 times the slab thickness or 18. It's just a number 18. So of the 3 requirements, this one is based on the load and these 2 are based on code maximums. Of these 3, the 18 is the least. So that's the one you have to follow.
And it need to meet the 3 of them?
I'm sorry?
The number we get needs to meet the 3 of them? Like the 3 parameters?
Yes, it's the least of the 3.
Okay.
Okay?
Yeah.
All right.
Wait, quick question, Professor. And it has to do with what he just asked. So we're comparing 3, 18.88, 27.5, but because 18 is due
The
to the
smallest.
ACI, and that's the smallest, that's what we're going with. So if, say for example, it was 19 or like 19.5, and we would use 18 from the ACI because 18 is where it would be the smallest from what we calculated.
Yes. Because what ACI is giving you is maximum spacing. You can't exceed that spacing. And the 2 criteria is 5 times the thickness or 18. So if the slab was only 3 inches thick, then your maximum would be 15. And if your demand was a lot higher, say like this number here came out to be 12, then that would control. It is whichever of the 3 is the least is the one that you have to provide.
Got you. Okay, that makes sense. And then so whatever we calculated, we're always comparing that to 18. So if we get a lower number than that, then that's what we're going with.
Yes. Yeah.
Okay.
Yeah. That works.
That makes perfect sense. All right. Thank you.
You're welcome. All right. Good night, everybody. Have a great weekend.
Thank you
We
so
will
much.
see you on Tuesday.